Good morning, everyone. So let me get started. Okay. So yeah. So we were talking about the base classifier. So now, whenever you encounter classifier kind of a design problem, when you want to choose a classifier, typically you won't have a lot of data, right? And you will be having a lot of features, but you may not have a lot of data, right? So in such a situation, base classifier is pretty useful. So you must always try to plot each of the features and see if there is any difference in terms of with what kind of histogram they observe and things like that, right? So that is one of the things that you must try, and then try to hypothesize whether indeed there is some prior, right? This is what we were discussing the other day. Probability, this is your prior, right? What is the ratio in which the classes are there? Then given that you are in certain class, what can you say about the features? How do the features look given that they belong to some class, right? So this is depending upon PDF, or if it is discrete, then it is P of capital. So this will be small x, for example. What is the probability that it is small x given class is 0? What is the probability that this is small x given? Let me just given that it is 1. So this is if it is discrete. If it is continuous, you will have densities. Okay, this will be a probability density function if it is continuous. Okay, and this is how you have, and what you will want to do is you have to estimate the posteriors. And posterior is basically, we represent it as q0 of x and q1 of x. Q0 of x is the probability that y is equal to 0 given x is equal to small x. And this is the probability. We define this as probability that y is equal to 1 given x is equal to small x. Okay. And we estimate the q0 using this formula. Q0 and Q1, you can get it by this formula. Q0 of x is equal to P0 F0 of x by P1 F1 of x plus P0 F0 of x. Okay. So I hope everybody understands the difference between F0 and Q0, right? So yeah. So if there are any questions in the notations or things like that, you can ask me now. Okay, so in the setup one, Mahendra, I have not yet seen your PDF. Perhaps if you have no class after this, you can just stay back, and then we can.
Okay, sir.
Yeah. Okay, so we looked at setup one. Setup one. So we were looking at a very single, like a very same example. We were looking at different setups. So the example that we were looking was of credit default problem, right? And for each of these setups, so first setup was the features. We don't have any features. This is empty set. Okay, and and then in setup one, setup two, I don't know if I interchanged it, but it might be set up 0 and 1 or 1 or 2. I don't remember. But anyway, so X here was taking values 0 and 1. 0 represents, 1 represents late taxpayer, right? And 0 represents early taxpayer. Okay. So we saw these things. And we were interested in minimizing what is called as probability of error. And probability of error is the probability that my classifier does not agree with what is the label assigned for a particular X. Okay, so this is what we saw. So now we want to extend it to one more case, which is setup 3, where we look at continuous features. Okay, so setup 3. So I have still not given you a proof of optimality of the base classifier. So just as a recall, HB of X is equal to 1 if Q1 of X is greater than or equal to Q0 of X, 0 otherwise. So this was the base classifier that we designed for setup 2. Okay. And for setup 3, now we have features X, which is in the range minus infinity to infinity. Okay. And what we are saying is that, so we looked at one case first where P0, so we looked at a special case where P0 is equal to P1 is equal to half. And we looked at a case where F0 of X is equal to normal with mean mu 0 and variance sigma squared. And F1, maybe I called it mu 1. I don't know. It is okay. I hope this is not going to be a source of confusion. We looked at this, and yeah, so we saw this, and when we plot this, you have a shape like this, right? So this is F0, and this is F1. So this is, let's say this is mu 0, the peak, and this is mu 1. Okay, and so the formula continues to be the same. Q0 of X is still the same formula. Okay, so Q0 of X is equal to P0 F0 by P0 F0 plus P1 F1. Okay, and so if you want to look at what is the region where if Q0 of X is greater than Q1 of X, what that essentially becomes, because P0, P1 are all half, it actually boils down to everything will get cancelled out. You will have e power minus x minus mu 0 by 2 sigma squared. Wait, so this has to be written a little more properly. Yeah, x minus mu 0 whole squared by 2 sigma squared. This is greater than e power minus x minus mu 1 squared by 2 sigma squared. So if you do all the algebra, like taking logarithm on both sides, and if you do the simplification, what you will get is x is less than mu 0 plus mu 1 by 2. Okay, so yeah, so this is what you will get, but this you could have got very intuitively as well, because if q0 is greater than q1 of x, what that essentially means is p0 f0 of x is greater than p1 f1 of x, right? Or f0 of x is greater than f1 of x. So if you just look at the density functions, and if you ask which is the region where f0 is bigger, so you will get a region, this region, right? And this is the region where the classifier is going to report 1. So we will call this as R0. R0 is the region where the classifier, the base classifier, is going to report 1. And this is the region, it goes till infinity. This is R1. And this point is nothing but mu 0 plus mu 1 by 2 by symmetry, right? Because the shape is exactly identical. So are there any questions here? So this is for the case where P0 is equal to P1 is equal to half. So if you change these numbers, all it does is it will change these ratios a little bit. You need to work out what exactly is the threshold, and you can just compute like this. You will get some threshold like this. So that's how you extend it for cases where P0, P1 is not equal to half. Okay. Are there any
Yes.
questions here? Yeah,
Sir, I had a doubt. Like for this, the sigma squares we have taken to be the same. So
yeah.
is that like because of P1 and P2 P0 and P1 being same, or is that true for all values?
No, no, this is for, I mean, we have assumed this is a special case, but if it is not the same, then what will happen? The shape will look different, right? So you will have one which is possibly like this, another one which is perhaps very sharp, right? Something very sharp. And then you need to find out which is the region where one is bigger than the other. So it will not be, if it is, so let me just try to draw properly. Yeah, something like this it would be, right? Yes.
Yes, sir. So that's just an assumption. Like it's not true that they should be same.
No,
That's
it
an
is not. It is not. It can be anything. No, it need not be even normal distribution. Normal distribution is an example that I'm showing so that you can understand how the base classifier is, what exactly it is doing, right? It need not be even normal, right?
yes, got it.
Yeah. And in fact, now I have taken just one feature instead of one feature. Suppose if there were multiple features, then you have to look at joint distributions. Okay, and then you have to ask like what is the base classifier there if you want to minimize the probability of error. Okay, so yeah, so this is what we have so far. So let me just briefly uh, uh, just say a few words about base classifier, at least now that you understand roughly what it is. I say roughly because we have still not seen the proof of optimality. So base classifier is a very powerful classifier, very less understood classifier. People typically jump to logistic regression, SVMs, neural networks, and all these things before they even look at very simple, trying to understand like what is the pattern that is underlying, that is existing, right? So you should, in at least now that you are familiar with this, even if none of your colleagues or if nobody else wants to try it, but you should definitely try base classifier first. You should try to see that given you are in a particular class, right? So if you are in the credit or no credit case, given that you are in a credit default case, you try to see if there is any differentiation in the spread of the features, the distribution of the features in a credit default case versus a regular case, right? Try to see if there is any interpretation, because this base classifier has a very nice interpretability, right? You can, if you design it well and if it works well, you can interpret your solutions better, right? So it is a very interpretable solution concept. So as a result, you should try out base classifier whenever you are given new problems. Okay. All right. So now let me do a few things, which is like the proof of optimality, and then we will try to do other things. Okay. So let's talk about proof of optimality for setup 3 first. Then we will generalize it for a more general base classifier. Okay. So now we have talked about probability of error. Okay, so probability of error, what is this? So this is equal to probability that my classifier HB of X is not agreeing with whatever is the label assigned for that, for a given X, right? So Y of X itself could be random. I talked about this earlier. So this could be random as well, right? So what we can do now is we will try to write this in terms of conditioning. So we will try to condition this. Okay. So what we will say is probability that HB of X um, is not equal to Y of X, given that Y of X is equal to 0, into probability that Y of X is equal to 0 plus, Okay, so now I want your help to try and simplify this. So what can we do? First thing, what can we replace this with?
Priors.
Yeah, prior. Okay, so we can replace this with priors, and then we can also say, yeah, so we can say, so let me just write the first thing as it is, and this we will call it as P0 plus this fellow as it is, and this as P1. Okay, so now, yeah, so now this is what is given. So now, yeah, so we have to estimate this quantity. So let us try to understand how to estimate what is the probability that HB of X is not equal to 0, yeah, or equal to 1, given Y of X is equal to 0. Okay, so yeah, so this is one thing that one we have to understand. So now first, when you are talking about this entire expression, we have written it as a probability, right? So what is the source of noise that is coming in? Where is the randomness happening?
In X and Y.
No, y I have fixed, right? I have said y of x is equal to 0. So
Only
y
Oh,
is
okay. In X.
X.
only an x, right? Only in x. Okay. In fact, that x is residing in the world where y is equal to 0, right? Only in x given y equal to 0. I am only interested in x, but not just in any x. I am only interested in x where y is equal to 0. And if I say this, what is the law that is governing this? What do I know about x given y? What is that called?
It is
So
a normal.
conditional density.
Conditional.
Yes, that is the conditional density. Okay, so we will write this as, therefore, so we can write this as some. So whenever I'm trying to estimate a probability given a density, what do? I integrate over a region, right? See, I don't know if you understand this, so let me explain once again. So there is a uniform random variable. Okay, so between, let's say, 0 to 1, and I want the probability between in this region, let us say A to B. How do I find out this?
Integrate conditional density.
Yeah, you integrate the density between this limit, right? Exactly, right? So here, whatever this probability is, it is some integration where I'm going to integrate f0 of x. Okay, and I will integrate in the region where my classifier hb of x is equal to 1. This will be small x. Okay. Does everybody understand this?
yes, sir.
Okay, good. So now, if I let's assume for the sake of simplicity that P0 and P1 are the same. So let's say that that's equal to half. So what I have is HB of x equal to 1. HB of x equal to 1 is R1, right? Right? R1 F0 of x dx plus R0 F1 of x dx. Okay, and let me just draw all of these things that we had represented earlier, just so that we can just look at R0 and R1 properly. Okay. Okay, so I will ask somebody, so everybody can see this. Can someone tell me in this figure? So whenever I'm trying to integrate a region, right, we are going to get some area under the curve. Okay. So can someone tell me where is this error lying? Where is this error lying?
The minus infinity to mu 0 plus mu 1 by 2. R1 is line. R1 is line mu 0 plus mu 1 by 2 to infinity.
Yeah, but what is the area under which I should shade?
Sir, from mu0 mu1 by 2 up to u1 mu1 for
No, it is not mu1, right? It actually goes, normal distribution always has something. It's not touching zero here. It goes on forever. Just that we can't see it, isn't it?
oh, yeah, yes sir, sorry.
Yeah.
But under
So
the first curve, that's what I mean.
under the first curve. So basically,
Yes, sir.
this is one thing. So you are under integrating f0. So this is the thing for this. Okay. And this double hash is for this. So is that okay? So this is what you will get by integrating these pieces. Now here we use the threshold as mu0 plus mu1 by 2. Now question may be asked, if I use some other threshold, what will be the error looking like? So let's try to do that. So if you have, let's say 1, and then you have the other one, assume that they are the same, I have drawn. So let's say we use this threshold. So this is my some R0 prime. Okay, it's a different classifier. It's a different threshold classifier, R1 prime. Okay, so now can someone help me draw the regions?
Yes, sir. We like draw a line vertically from that.
Okay. Shall I take it all the way up?
Yes.
Okay. Yeah.
So for the first error, it will be the part to the right of that line under the first curve.
Okay. So let me draw that. Okay. Okay. And
then for the second, it will be the part to the left under the second curve, like the big one.
the big one. Okay. Okay. So now is the proof of optimality clear? At least for the special case where P0 is equal to P1 equal to half, is the proof of optimality clear? If it is clear, can someone tell me how is the proof of optimality clear?
Yeah, that area will always be the smallest, the first one.
Yeah, because this classifier, which is based on some other threshold, has this same shape, right? This error is anyway there, but in addition, it has this extra, like a triangular shape is there, right? This is an extra error. So let me try to highlight that. So this region that I'm shading again in black, this is an extra error in comparison to this, right? So this comes out as an excess. So as a result, what happens is we are actually getting lower error in the base classifier against any other threshold based classifier, for at least in the two case problem. Okay. Is this clear?
Yes, sir.
Okay. How about the others? Can you say it in chat?
Yes, sir.
Okay.
Sir,
Yeah.
I would like to ask, like last day you was telling about false negatives and something false positive.
Mm.
So
Yeah.
you can tweak this like threshold to reduce false negatives and increase false positives.
Yes. 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 So yeah.
Might,
So tell me.
so I was asking, this might be intentional, like we intentionally can shift this threshold position.
Yes. Yes. So that is something called as Neyman-Pearson classifier. Okay. I don't know what is the spelling. Maybe it is this. Okay. Neyman-Pearson classifiers. So this is like a very World War II type of a classifier. Okay, it was very useful. It is still very useful. What you want to do is you want to control the type 1 error and try to find out, exactly what you said, Divyansh. So this is actually, let us see, we may just, I will probably ask you to implement this in your this week's assignment, which I will release soon. Okay, so I will probably ask you to implement some of these things. So basically, what is type 1 error? So let us just try to talk about type 1 errors and type 2 errors. So I'm just talking about this just because he asked. So this is probability that HB of X is equal to 1 given Y is equal to 0. Okay, so this is false alarm. Okay, so now in this, can someone tell me which is that region? HB of X is 1, but I am saying actually the Y is 0, but I am saying HB of X. So which is that type 1 error?
Right one.
Left.
Who is saying right and who is saying left? Can you do it in the chat? All people who say right, say right. So right means there are two parts, right? So there right of this here and left here. So this is so this one region, this is one. So this is the right, this is the left, right? So which one it is? So can you say in the chat which is the type 1 error? Is the question clear? Nobody is saying anything. Okay, so Gunjan has sorry Nikita has said right. Okay. So let me go back to this so that you can all see. Is there anyone who thinks it should be left? I mean, see, it's nothing wrong. I mean, I'm not saying it's right or wrong, but if you have any reason why it should be left, you let me know. We can discuss it. Right. So, but let's try to understand. No, when Y is equal to 0, I am only interested in F0. So I should be looking at F0 curve, right? Because this is the distribution of the features given Y is equal to 0. So when you look at this, I am interested in HB of X being equal to 1. So HB is not correct here because I am writing for this some classifier. So let us say H of X. So this is a H of X classifier. Okay. So then this is this region, right? So this is the region where I am reporting 1. Okay. So this is false alarm rate. So likewise, type 2. Here now very analogously, this is equal to 0 given Y is equal to 1. This is called as missed detection. Okay. See why is it called false alarm and missed detection? Can someone, I mean, I told it's World War II, right? So can someone maybe think of it? I mean, it's so obvious, right? See, you have a radar. Okay. So you have a radar and possibly you are looking out for missiles, right? You're looking out for incoming missiles. And if you wrongly say that there is a missile coming in, you raise an alarm, there is no missile, this is false alarm. Okay. And if there is a missile coming in and you don't say anything, it's a missed detection, right? So that's the reason why these names have been kept like this. Okay. So this is one concept. So now so if you look at the expression here, right? So basically it is P0 times type 1 error plus P1 times type 2 error. So basically what you have is P of error is equal to P0 times type 1 error plus P1 times type 2 error. Okay, and what Divyansh was saying is if you fix this, what can we do? Yeah, obviously. So if you fix this and if you fix this, you can control your overall error. If you are more careful about type 1 error, you don't want to have too much false alarm, you can control this. You can set your classifier so that this is controlled, and then as soon as you do that, this will be this will be set to a value, and then you have that desired thing. So yeah, so I will ask you to do what is called as receiver operator characteristics, ROC curve. Okay. Operator, I hope it is, or operation characteristics, maybe, whatever. So ROC curve is a plot of one of these parameters versus another one, and then you get some smooth curve. Basically, when you tweak what threshold you want for one of this, the other one is automatically fixed. Okay, and what the base classifier is trying to do is trying to minimize the overall thing. Okay, so anyway, this was like a small diversion. So let's come back to the original problem. So what we have here is this. So what you have here is that probability of error is equal to this. Okay, so I hope everybody can understand this. In fact, what I will say for base classifier, suppose if I put probability of error of base classifier, what I can actually say if P0 and P1 are same, I can say this half times, I will not write HB, I will just say minimum of F0 of x, comma, F1 of x dx. Let's write this as small x. F0 of x, F1 of x dx. Okay, so that's what we did, right? So like if you remember, I integrated this region, and so that is minimum of at this for this portion, this is a minimum, and for this portion this is the minimum, right? So that's how we did it. So this is the, like, more formally, if you want to say this is optimal, this is the way to show it. Okay, so does anyone have any questions about optimality or any other topics that we discussed so far? Yes, no? Is it clear?
Sir, so you mentioned that that ROC thing. So it basically like gives a correlation between type 1 and type 2 error, right?
Yeah, you can operate your classifier in as one of the points on the ROC curve.
Okay,
When you
so
change
like,
the threshold, it will move in the ROC.
so like if we have the ROC, then can we find like the optimal position for the threshold?
No, it is generally not. I mean, so this, when it is two-dimensional, like a single-dimensional feature, yes, maybe. But in more complicated situations, it is not that easy.
Okay.
Yeah. Okay, so yeah, so now let us look at a few more variations, and then we will conclude this topic. Okay, so yeah, so now let's talk about variation 1, where let's try to generalize this to a different case. Okay, so suppose my y is not just Z2 class, but let's assume that there are some k classes. Okay, so let me call it, just so that we can distinguish, let me call it C1, class 2, class 3, all the way till class M maybe. Okay, so there are M different labels. Instead of just 2, there are M labels, and my output h of x, like my classifier, can have different outputs. So I can have alpha 1 for C1, alpha 2 for C2, okay, alpha m for CM, and I can have more. Okay, what is that more? So let me, instead of m, I can have some k, right? So I could do like that. So what is the point of having k not equal to m? So examples of this case is, first is k is equal to m, and alpha 1 corresponds to c1, alpha 2 corresponds to c2, all the way till alpha m corresponds to cm. This is like your usual classifier. But I can have for another example where k is equal to m plus 1, okay, where alpha 1 to alpha m are the same. This is the same. So okay, oops. What did I do? This is the same, whereas alpha m plus 1, this is actually the case where I want to say not sure, right? Or yeah, so I can have a situation like this where my classifier would like to say, if it is not able to tell very clearly either of these things, it wants to say something else, then it can have something called as not sure. Okay. So in general, 1 and like k and m may be different, right? So I have gone from the binary classifier to a m class classifier. Each label will have one of m different labels, and my classifier can report what that label is, or it can report something else. Okay, so this is like a more generalization into a multi-class, and the classifier outputs need not correspond to the class labels also. So it's a very general setup. Okay, so and then I need to be able to tell. So we had probability of error in the previous case. Now what we will look at is called as what is called as loss function. So we will define what is called as loss function. So this is something like Divyansh was asking, no? How do you control type 1 error, type 2 error? If type 1 error is more costly than type 2 error, then what do you do? And things like that, right? So for that case, we define a loss function where it's a function from, so yeah, so this is your this whatever values y can take, I will call it as script y. Okay, so this set is script y, and all these things I will call it as an action space a. Okay, so loss function is a function from action space cross y to r. So yeah, so basically what it is trying to do is, like, suppose example, let me give you an example. So let us say y is equal to 0 1. My action space is also 0 1, and suppose L of small a comma y, okay, is equal to 1 if a not equal to y, 0 otherwise. Okay, so this is called as 0 1 loss. So what does this compute? So yeah, so this is 0 1 loss, and now if I try to compute the expected loss, of, sorry, h of x comma y, right? If I try to do this, this actually turns out to be probability of error, right? So basically I make an error whenever whatever I report does not agree with y. Okay, is everybody able to appreciate this, how this is working?
Yes, sir.
Yeah, so loss function can capture your probability of error. All you need to do is you make an error only when they don't agree. Otherwise, you say there is no loss, right? So this, when you try to minimize, you end up minimizing probability of error. Okay. So in general, you can have a loss function which is not necessarily corresponding to a usual classifier where the labels and the actions, they match each other, but you can have anything otherwise, right? You don't have to have them similar. For example, you can have a setting where there is a not sure option. Okay, All right, so having described this in little bit detail, so let's try to look at the base classifier in this case. Okay, so the base classifier here. So what should the base classifier do? Can someone make a guess? So you have a loss function, you have an expected loss function. So let's say R of H is equal to expected value of the loss of your classifier. If I tell you this, so what should be the base classifier? HP of X. How do I define that? So how did we define in the previous case? So we said that P error of H, right? And I said arg min over H, right? And this I called it as HB, correct? So in the same way, what do you think we should do? I mean, at least to define notationally, in terms of notation, it is very obvious, right? You just say argmin of R of H. You try to find out that H so that it minimizes the risk. So this is called as risk, okay, risk of the classifier. Expected loss is called as a risk of the classifier. It's just names that has been given in the statistical learning theory. These are the names that are given. It will come again and again. So you better get comfortable with these names. Okay. So this is called as a risk of the classifier. All right. So now defining the name is fine. So we should still have a policy on how to define it, right? How to actually use it, right? So that's what we will do next. So this is going to get a little algebraic. So before I go there, are there any confusions related to how the setup is there? So is there any questions in the setup? All right. So let's get into the details then. So the first, so I have to do some recap, okay? I don't know if everyone understands this, so recap. So this is recap of iterated expectation computation, right? Iterated expectations. So can someone explain to me this, or some proof, or have you seen this at least? You have seen, I know math and CS students have seen, but how about electrical students? Have you seen this formula? Sneha, have you seen this? Do you remember?
Yes, sir.
Okay. All right. So so all of you have seen this. So let me try to just give a brief recap of this, right? So what is the meaning of expected value of X given Y? So maybe one of the electrical students can explain this. So what is this? What does this mean if I say this?
So expected value of X when it is conditioned on the Y as a random variable.
Okay, so it's a so Y, so condition on Y, which is also a random variable. So is it a is it a number, or is it what is the thing? I mean, does it, how does this change? Does it change, first of all, expected value of X given Y? So let me give an example then. So perhaps that should jog your memory. So you have, let's say, X height and weight, okay? And I can't draw, like, imagine that there is it's a 3D shape, okay? I'm drawing the density, which is having a shape like this, right? So these are all the contours. Because, you know, if someone is typically very tall, if someone is very tall, then their height also may their weight may also change, right? So this is weight, and this is let's say height. Okay, so now suppose if you have a figure like this, right? So I don't know, so maybe if it might help you to visualize it like this. So there is a hill like this. Yeah, so now what we are saying is I will fix a particular height, right? Let's say I will fix a height. So let's say y is equal to small y. Then I will, so once I fix this y equal to some height, I will get the distribution of x. So if I look at distribution of x given y is equal to small y, I will have some shape like this. Okay. Whereas if I take a lower y, then my peak may change. Right? Something like this. So expected value of x given y is the mean of this. Okay. And now when you vary y, expected value of x given y changes. So expected value of x given y changes when y changes. Okay. So therefore, you can treat expected value of x given y as a function of y. You can treat this as a function of y. Okay. So when I write something like this, what I'm actually trying to say, when I'm trying to do expected value of x is equal to expected value of x given y, I'm treating this as a function of y. So basically this will become integral. If y is a continuous random variable, it will be integral. Expected value of x given y is equal to small y, and what it will be here, the density of y, fy of y dy. Okay, and if expected value of x given y is equal to y, if you want to evaluate this, what you are going to here, what is the thing that is random here? Can someone tell me?
X.
X is random.
X is random. So basically, I will be integrating x, but I will be integrating x with respect to the case where y is equal to y. Okay. Dx. And this one, if you remember, this is nothing but fxy of xy divided by fy of y. Okay. So if you put all of these pieces together, let's put all of this together. So what you will get is expected value of x will be equal to double integral f dx, okay, into fy of y dy, and you can cancel this out, and then you will get okay. So this is nothing but the definition of E of x, right? This is the definition. When there are multiple random variables, and if you want to find the expectation, you have to integrate with respect to the joint, and then you'll get this. Okay. So this is just small recap. Okay. So now when you come to risk of a classifier R of h, so how do we use this? So R of h, you can define this as expected value of L of hx y. Okay, this can now take values C1 to Cm, and this belongs to action space A. Okay, so this is what we have. Now what we will do is we will condition this as expected value of, I will condition on x. So this will be y given x Okay, so this is what we will do, and yeah, so that ends up becoming okay. I think I am. Is this okay? Yeah, so we can define it like this. There is, I hope I have not done any mistakes in terms of x. Yeah, this is fine. So this is what we will define the risk of the classifier R of x like this. Now what we are going to say is that base classifier, so we will continue this tomorrow, but let me just give you a hint where we are going. So what base classifier does is that for every x, okay, for every x belonging to my feature space x, what it will do is it will choose HB of it will choose HB of x to be equal to some action alpha, let's say j, such that alpha j is going to be equal to argmin of this expression, of argmin of this expression. Argmin of let me just say this expression, okay, argmin of this expression. So that means I will fix hx equal to some alpha j, and I will do this. So anyway, tomorrow I will explain this again. So we will look at a small example about this, and then we will stop here. But I just want to talk about this week's lab assignment so that we can get that started. So so we will come to this. This is a little bit of a theoretical exercise. So if you are so far anyway, what we have discussed so far, I think it should be okay to you. So until here, there should be no problem. Here, this is a new thing that I'm defining, and I am sure notationally there should be no confusion. This particular aspect about how we choose this, I will explain tomorrow. But let me just talk about this week's lab assignment, which is called as naive Bayes. So we looked at a case where x was a single feature, right? So your capital X, this was a single feature. That means I looked at only one aspect of the credit default problem. I looked at only one aspect, which is the difference between what time the person pays tax, and so that's what we looked at, right? Minus infinity to infinity. What time the person pays tax versus the reference time. So that is what we implemented. Now, what if there are multiple features? So suppose x is a vector. That means there is some x1, let's say x1 and x2. There are two features, for example, and I would like to predict some output y looking at the two features. Okay, so y can be, for example, let me give you an example of male and female. Okay, so there are two features, and there are two class labels, male and female. So now, if you have something like this, how do we extend everything? What is the one change that will happen? Priors, is there any change in priors? Definition of priors?
No, sir.
Yeah, priors will not change. Okay. What about class conditional densities? How does the class, is there any change, or how does the class conditional density change?
We will have them for x1 and x2.
Yeah, so now, yes. So class conditional density F1 will have two things, x1 and x2. Okay, F0 of x1 and x2. This is going to be the joint distribution, right? So let's say x1 equal to small x, x1, and x2 equal to small x2, given y is equal to 0. And similarly, you will have two things, right? Okay, so this is how the things will change. Now, what naive Bayes assumption is, okay, so using the naive Bayes assumption, what we are going to do is that we are going to assume that this is actually equal to P of x1 equal to x1 given y equal to 0 into P of x2 equal to small x2 given y equal to 0. Okay, so I think we are running out of time. Maybe somebody is reminding me of that. But we will do this, and this is called as naive Bayes assumption. Everything else will remain same. You are going to predict HV of x equal to 1 if the Q1 of x is greater than Q0 of x. So this is the entire thing remains the same. You are just going to make this assumption because then estimating this class conditional densities will be easier. Okay, so you will do this as part of this week's lab assignment. Okay, so let me just stop here. If you have any questions, you let me know. Okay, all right, thanks everyone.
Sir, you mentioned like when data is less, then base classifier becomes helpful. So how is that?
No, because if data is less, if you plot the data, if it turns out that it is looking like Gaussian, so already you are able to make reasonable confidence, right? So if it looks like Gaussian with whatever little bit data you have, then making a sound assumption like this might be useful.
Yeah, but like in general case, predicting the distribution, probability distributions can be more difficult than other classifiers in this. Like we have to learn the distribution for probability.
So, okay, so you see what many times when you are looking at various classifiers, like for example, you want to predict using, so you have this variable devices like something to measure heart rate or oximeter and things like that, even blood pressure, things, many of these things are biological. So whenever things are biological, there are certain distributions that it already is known to follow, right? And then when you look at customer arrival, suppose you are running a e-commerce firm, when you look at customer arrival, you know that the arrival will be exponential between one customer and another. It will be exponential, or if you collect customers in an hour, it will be Poisson. So if you use the knowledge that you have on the problem, it might actually be better to use Bayes classifier, because then you are explicitly modeling your knowledge. In that sense, I was saying. However, if you don't know anything about the problem, then you are anyway in a fix, right?
Like that becomes another.
Yeah. Correct. If you know the problem well and if you are able to model it, then using Bayes classifier is better because you're explicitly modeling your knowledge. That's what I meant.